All right, now we get to start our 4-chapter study of the periodic table of elements, atoms, parts of the atoms, chemical bonding, and chemical reactions. Some detail about all of those coming up in chapters 3, 4, 5, and 6. Periodic table looks intimidating at first, but you'll find that although there's a whole lot of different pieces of information on that chart, each one is fairly easy to learn. The tricky part is having to remember so much at one time. That's why we're going to take 4 chapters to go through it all, starting with atoms, atomic models, and the parts of the atom. Are we ready? First, this large hardened collidor. What is that? This is a very large building built along the border of France and Switzerland for a specific purpose. This is the world's largest machine, measuring 27 kilometers long, 16.77 miles long. That's a very long corridor, and what's the purpose of it? This large hardened collidor is used to examine atoms and subatomic particles by smashing the particles together at the speed of light, almost 300 million meters per second, approximately 186,000 miles per second. In scientific terms, get a color that will show up well on this dark background. 300 million is 3 times 10 to the 8th meters per second. That's not the exact speed of light, but it's very close. It's more like 299 million and some change. That would round up to 300 million. But this is the number we use in calculations, especially at the introductory level, to make things a little simpler to follow. But that's very fast. Here is the English version right here, about 186,000 miles per second. That is fast. Ready? Atomic models, and there are many, and many that changed over years, decades, and centuries. Remember, models, many of them are workable, meaning altered or revised as new information became available. Ancient Greek philosophers, such as Democritus, called the very smallest possible particles atomos. That's a Greek word, atomos, which means indivisible. So at one point, atoms were thought to be completely indivisible, cannot split apart into smaller parts. We now know that that is false, but these particles in English are called atoms, which comes from that Greek word atomos. We now know that atoms can be divided, and that's where we get our study of protons, neutrons, and electrons from. There are other subatomic particles too that you'll learn about in higher levels of chemistry and physics. We will deal with the basic 3, protons, electrons, and neutrons. Ready? The law of definite proportions. What you see here is a picture of a waterfall. Hopefully that shows up pretty well for you. And we know the chemical formula for water is H2O. This means every molecule of water has 2 atoms of hydrogen and 1 atom of oxygen. Now, each atom has its own mass as well. Let's, for now, use the unit grams. If you look on the periodic table and round off the decimal, you'll see that the mass of hydrogen is 1 gram. Now, it would take a certain number of atoms called a mole to get 1 gram of mass, but that's something we're going to discuss a little later on. And remember, we have 2 of those, so that's 2. So the total for hydrogen is 2. If you look at the mass of oxygen, you're going to see 16. And there's only 1 of those. So if we add these together, then we get a mole of water, which is a specific number of molecules. I'll go ahead and say it. 6.022 times 10 to the 23rd power molecules of water. That will have a mass of 18 grams. Definite proportions means this is going to be put together in exactly the same way every single time. So water is always going to be H2O. Therefore, water will always have a total of 18 grams for a mole of molecules. A single molecule will have 18 atomic mass units. Now, every compound has a definite composition of mass because every compound has a definite makeup put together exactly the same way every single time. And as we do more, especially a couple of chapters from now, when we talk about gram formula mass, that will become even more evident. Once again, though, every 18 grams of water has 2 grams of hydrogen and 16 grams of oxygen every single time. So let's just multiply these by 10 and say we have 180 grams of water. That means we're going to have 20 grams of hydrogen and 160 grams of oxygen. And that multiplier would affect the numbers in exactly the same way because of the exact ratio and proportions. Ready? A scientist named John Dalton theorized 5 properties. Now, 4 of these 5 items that you'll see we still believe to be true. 1 of them has been found to be false. 3 on this page, the other 2 on the next page. So in approximately, or actually in 1803, John Dalton discovered these 5 properties. Elements are made up of atoms, which we still believe is true. The smallest part of an element that has the same properties is called an atom. Number 2, atoms are indivisible. This is what Dalton believed, but was shown later that atoms can be divided. So that's why I have false after the word indivisible. Atoms cannot be destroyed. That is still true. That's the law of conservation of matter that we've talked about before. The atoms of a single element are all alike, except for the number of neutrons in some cases. But for example, we mentioned oxygen a little while ago. Every oxygen atom has 8 protons and 8 electrons before combining with something else. The number of neutrons will vary. Most will have 8, but neutrons, as we'll talk about, I believe in the next set of notes, that's going to vary. So these are the first 3 parts of Dalton's theory, and notice the first half of number 2 we now know is false. Ready? Parts 4 and 5 of Dalton's theory. Atoms of one element are different from atoms of other elements, especially by mass. And probably the biggest example that I can think of offhand would be an atom of chlorine, which has 17 protons. There's a reason why I make sure I put the 17 there that I will explain another time. And right next to it, to the right, is an atom of argon gas, 18 protons. Chlorine gas is a very, very, very deadly element. If you sniff chlorine gas directly from a container, you may very well drop dead instantly. However, argon gas, that one little extra proton, makes this element completely safe. And that is found in many neon signs and also in insulated windows. You might hear the commercials, buy our windows and keep your house cooler in the summer and warmer in the winter. Argon gas is very good at blocking the flow of heat. But very deadly chlorine, very safe argon, the difference is just one teeny tiny little thing called a proton. The mass will be different too, because argon has a little bit more in the neutrons than the chlorine gas would, and of course an extra proton, which would also mean another electron. So the masses will be different. Part 5 of Dalton's theory. Atoms combine chemically in small whole number ratios. We just showed you that on the last page where I wrote H2O on the page with the picture of the waterfall, okay, 2 pages ago. But the definite proportions. Every compound is made up exactly the same way every time. Of course, we know water. Here's water again, H2O. Here's another one you're very familiar with, sodium chloride. Glucose, C6H12O6. This is one kind of sugar, and notice compounds are exactly the same way every time. Now here's what I think is really cool about chemistry, atoms, and the periodic table. We mentioned chlorine a moment ago, very deadly substance. Really, one sniff of chlorine gas directly from a container can and most likely will kill. Sodium is a very explosive metal. When dropped in water, weight just a tiny bit, We might see a flame and then a small explosion. Of course, a larger chunk of sodium in water will give you a bigger explosion. But these two come together and then make a compound that we eat all the time. Hey, pass me the salt. Put that on my fries. That's table salt. That's what we eat all the time. Hydrogen, when put next to a flame, hydrogen by itself, and there's a reason there's a 2 there, that will explode. Fires need oxygen in order to burn. Here's some room here. And that's an O2, and again, I'll explain that another time. But very flammable. And at room temperature, those are both gases. Yet water at room temperature is a liquid that puts out fires. So you can see combining chemicals very, very much changes those properties. Atoms combine chemically in small whole number ratios in definite proportions every single time for a compound. Ready? Electric charges. There are 2. One's called positive, one's called negative. Nothing fancy or magical about the names, just 2 charges that do opposite things, so somebody gave them opposite names. 2 electrical charges acting in opposite ways were given those names, positive and negative. Now, one part of the atom will have the positive charge. One part will have the negative charge, and the third part has no charge at all. The same charges together have been proven to push each other apart. They will repel. And you hear the law of charges. Like charges repel, unlike charges attract. The different charges put together attract. So if we put one positive charge next to one negative charge, they're going to come together. And as we'll learn not too long from now, sodium with a positive charge, and we'll explain how that happens, will attract to chlorine with a negative charge. And the combination drastically changes the chemical properties of those 2 atoms. But if you were to put 2 protons together, those are going to repel and push each other apart. Same charges will repel, or also called like charges. Different or opposite charges together will attract, and that's called the law of charges. Ready? Electrons. We'll talk about those first. You see the picture there. What is an electron? A very stable elementary particle that has a negative electric charge. Where do you find those? Look at the picture. See the arrow pointing? You're going to find those on little circular paths, kind of, not exactly, but kind of like the planets orbiting the sun. The electrons will orbit around the nucleus. And we'll talk more about the nucleus in just a bit. Electrons were first discovered in 1897. And again, the electrons have the negative charge, and they are teeny, teeny, itty bitty little guys, the smallest of the 3 parts. The electrons have that negative charge, and really it's the electrons that will determine how atoms combine with each other. Even more so, let me add a word to the word electrons. Valence electrons, which are the ones the furthest away from the nucleus. So here you see one a little bit closer. Here you see these furthest away. Valence electrons are the electrons that are on the furthest away or the outside energy level of a particular atom. It's the valence electrons that cause atoms to combine with each other. First discovered around 1897. Ready? Professor Joseph John Thomson realized that electrons are parts of those atoms, and he did some experiments with those. Kind of just call him Thomson when we refer to him after that. Professor Joseph John Thomson realized that electrons are parts of the atoms. He also noticed that since a full atom is neutral, atoms must also contain the same number of protons or positive particles that were later called protons. So let's go back to that chlorine atom. So Thomson discovered that chlorine has 17 electrons. And by doing experimentation, he noticed that we have a total net charge of 0. Well, if electrons have the negative charge, there's only one way that we can end up now getting a total overall charge of 0 or neutral. Let's just do some integers. Negative 17 plus what equals 0? That would be positive 17. And further experiments on many different atoms led Thomson to realize that all atoms are neutrally charged when they're by themselves. So that means every atom has the same number of protons as it does electrons. So let's look at an atom of calcium, whose atomic number is 20. The atomic number is the number of protons in an atom's nucleus. So the question may be, how many electrons does this calcium atom have? That's going to have to be, to match 20 protons, how many electrons would give us a total charge of 0? Remember, that's a positive. That's a negative, would have to be 20. Now, when atoms start to combine, then the number of electrons will change, and that's coming up later on. Ready? Okay, this plum pudding model, remember we're talking about Thomson, J.J. Thomson. Electrons move randomly within a sea of positive charges, kind of like plums being stirred in pudding. You make up some pudding, now you want to put your plums or raisins or whatever. You drop those in and just start stirring. What that's going to do is cause all those plums or raisins or whatever you put in, blueberries, strawberries, who knows what, they're just going to start moving around in all different directions based on how we stir. If we stir in circular patterns or crisscross or whatever, the electrons are just simply going to keep on moving around with really no set pattern to go. Now, later on, it got discovered that electrons do tend to move more in a circular orbital path, as you saw a little while ago. But at least this was a model to work with. J.J. Thomson, for emphasis, move that out of the way, is credited with the plum pudding model. But again, we know now that electrons do have a more definite pattern. Ready? Let's look at a quick, brief nuclear model. Another scientist named Ernest Rutherford, who did something very, very important to the study of atoms. He discovered positively charged particles and uncharged or neutrally charged particles together in the center of the atoms. I had to pause for a moment. Saw an error that I went ahead and corrected. So Ernest Rutherford, by doing experimentation with atoms, discovered the positively charged and uncharged particles together in the nucleus. Of course, we know now that the positively charged particles are called the protons. And you can kind of see a T right there. Looks a lot like a plus sign. Uncharged or neutral charge led to the name neutron. So Rutherford, doing what's called the gold foil experiment, which you'll see in just a moment, discovered these two kinds of particles in the middle of the atom. Ready? And here's a picture of that gold foil experiment. Now look as you see. Here's your particle emitter. Alpha particles are 2 protons and 2 neutrons. So let me go ahead and put that on here. Something that's going to come up later on anyway. An alpha particle contains 2 protons and 2 neutrons, and that's being shot toward a sheet of gold foil. Think of aluminum foil that you wrap up your leftovers with. Well, this is gold instead of aluminum. Now you'll notice, put the words up, Rutherford shot these alpha particles into the gold foil, and look what happened. These back here represent the particles that went straight through, because remember, atoms have a whole lot of empty space inside them. There's absolutely nothing between the nucleus and the electron levels. So atoms are able to pass through each other fairly easily. But then you see right here, this represents bouncing off the gold foil. Well, then there has to be something in the middle there that's deflecting these alpha particles away. Most of them, again, went through the foil without being hindered in any way, but some bounced off and pretty harshly, hit hard like throwing a golf ball up against a concrete wall. Our walls in the classroom are made of concrete. If I threw a golf ball off that, that ball's going to bounce off and probably come back to us almost as hard as we threw the ball in. So there has to be something that's deflecting these alpha particles away. What this showed was very dense particles in the center of the nucleus, and further experimentation led to the discovery of the positive charges on some of those things, called protons, and the no charge, the neutral charge, on the other particles, and those are called neutrons. The protons and the neutrons make up the atom's nucleus, and the protons and the neutrons make up the atom's mass as well. A neutron is actually a proton stuck to an electron, so two of those put together. The difference in size and mass between a proton and a neutron is the electron. And that electron's mass is so small, it's been rendered insignificant. So when we add up the protons and the neutrons of an atom, we get the atom's mass. And although we're not really doing it, we get to kind of ignore the mass of an electron, because the neutron is actually a proton plus an electron together. Okay, more about that coming in a little later lesson. Ready? The nucleus. The electrons orbit around the nucleus. So the electrons spin around and around and around outside the atom. Those protons and neutrons are held together in the center of the atom. Kind of like the sun, the center, remember, geocentric, of all the planets orbiting around. The protons and neutrons are held together in the middle, but realize something. All the protons have positively charged particles. What's keeping those like charges from repelling? That would be the neutrons. The neutrons are just massive enough to block that electric flow of like charges that should be repelling but don't. There's enough insulation in the neutrons, and in many of the atoms there are far more neutrons than there are protons. So it kind of neutralizes or controls that static-like charge. Again, there's much empty space between the nucleus and the energy levels. In fact, if the nucleus was about the size of your fingertip and you stood right in the middle of the football field, you put a pen cap that's about the size of your fingertip down there, the first electrons would be well past the end zone. Neutrons and protons have almost the same mass. Okay, I'm going to pause for a moment and I'll be right back. And that's a good thing about the pause button. When you watch the video, very, very little pause actually happened. The electrons orbit around the nucleus. The protons and the neutrons make up the nucleus. There's a whole lot of empty space between the nucleus and the first level of electrons. And as I said a few moments ago, neutrons and protons have almost the same mass. And once again, the difference is the electron. A neutron is actually a proton and an electron stuck together, but because of the significance or the insignificance of the electron, to get the total mass of an atom, we just add the protons and the neutrons, and we don't have to worry about the electrons at all when dealing with the mass. And that is why. Ready? Oh, the nucleus is very, very small compared to the size of the entire atom. 1/100,000th the size of the atom. That shows you that the electrons are really far away from the nucleus. Remember, nothing but empty space between the nucleus and the electron levels. Now we're ready. Bohr models, which we're going to practice doing, show us the center of the atom, the nucleus, the energy levels, and the electrons. Now this picture is a little bit fuzzy, but you might be able to see the symbol AU in the middle. That's the chemical symbol for gold, element number 79. The numbers at the top right read 2, 8, 18, 32, 18, 1. Those are the electron level configurations. The electron configuration on each energy level. And I'll go ahead and write these a little bit better for you. 2, 8, 18, 32, oh, running out of room, so 18 and 1. The first level is the one closest to the nucleus. So this would be the first level. And realistically, it gets more complicated than what we're going to do in this introductory level class. When you get into chemistry class, you'll start talking about sub-levels as well. And you see the 2 electrons on that first level. And I won't do all of them, but the first couple. And here you have 1, 2, 3, 4, 5, 6, 7, 8. So we got 2 on the first, 8 on the second. And then we have 18 on the third, then 32, then 18, and then 1 out there on the outside. This one is the valence that I mentioned a little while ago. The outside electrons on the outermost energy level are called valence electrons, and those determine what the atoms do with each other. The element symbol goes in the middle. So the symbol for gold is AU. You might also see, instead of just the symbol AU inside the nucleus, you may actually see something like this. In this case, 79 protons and the number of neutrons, which would be, in this case, 197. And then we would add all those up to get our total mass. 16, 17, 276 atomic mass units, just by adding those up. Ready? All right, photons. What are photons? Photons are not really particles and parts of the atom. Photons are energy that the electrons give off. And as you see the picture here, on the top left of the picture, you see photon with a little red swirly arrow. Photons are actually amounts of energy, and typically different colors of light that come off the electrons. And photons get released as energy when electrons move around. Okay, look over here. In the middle, you see electron jumps to higher shell. So the electron is going from the first, they drew it this way, to the second. Now what that does is give the electron more energy, and then that energy is released as different kinds of radiation, including different colors of light. And now you see the photon has returned back to that first level as that energy is released. The valence electrons cause atoms to combine with each other. The electrons closer to the nucleus, those are called core electrons. They're going to cause other things to happen, things that we're going to talk about little by little at other points of the year. With photons, electrons jump from a lower energy level to a higher. It might be the first level to the second, or the second level to the third, and so on. And then those electrons lose their energy, and when they do, if this one jumped out here to the second, would immediately jump back there to the first. But remember, the orbit continues, and that's why you might see that here in a different position. They'll fall back to that lower level that they came from. So electrons gain energy, jump a little further away from the nucleus, release that energy, and then drop back down to where they came from on the lower energy level. The energy given off as photons, which are packets of light energy. Now, not all light is visible. The colors that we see come from photons, but there are invisible forms of light that do different things and serve different purposes, and some of that can be very dangerous. And we'll talk about electromagnetic radiation and different light waves much later on in the year. But photons are the energy released when electrons go up in energy level and back where they came from. Ready? And that'll do it for this lesson. Next time we'll talk a little bit more about protons, electrons, and neutrons, and their functions and what to expect from them. Thank you, and good night.